So, welcome back, and this is lecture number 52 on existence of Laplace transform. So, in the previous lecture we have seen that some elementary functions we can use in this integral, which is the Laplace integral, and a closed form of the solution can be obtained, or this integral can be evaluated. So, we have evaluated several Laplace transforms, or the Laplace transform of several elementary functions, which include the exponential function, the polynomials, so t power n, and the constant function 1, etc. So, in this lecture we will be talking about, in a more general context, that what are the conditions under which the Laplace transform exist. So, we will be talking about the piecewise continuity of the functions, because that is required as an sufficient condition. We will be also talking about the functions of exponential order, and then finally, what are the sufficient conditions for the existence of Laplace transform. So, the existence of Laplace transform, if we consider for instance e power t square, such functions e power t square, and try to compute this integral, this improper integral 0 to infinity e power minus s t and e power t square. So, we are trying to compute this Laplace integral, but what is happening in this case now, because exponential here is like t and t minus s t, and this integral is over 0 to infinity. So, this integral does not converge for any choice of this s, whatever s, how large s we take here, but so this is t minus s. So, whatever value of this s we choose, this will never converge. So, just to recall what are the conditions, the necessary conditions rather than for the convergence of such integral. So, the divergence test we have for such improper integral, which says that if the tail end of the function does not approach to 0, that means if we compute the limit as t approaches to infinity, this f t of the integrand, and if this does not go to 0, then this above integral will diverge. That is the basic test we have for the divergence of such improper integral. So, if this f t does not go to 0 as t approaches to this infinity, then definitely this integral will diverge, and this is exactly happening here. So, if we look at this f t, I mean the integrand of this, it is e power t and t minus s. So, if we talk about this limit as t approaches to infinity of this e power t and t minus s, so whatever value of s we choose, when this t approaches to infinity, this will go to infinity, it will never go to 0, because of this t minus s factor here, and t can be very, very large. So, t is approaching to infinity. So, whatever s we choose there, again when this t approaches to infinity, this can never go to 0. So, therefore, because of this divergence test, we know that for any value, any choice of this s, this integral, the Laplace integral diverges. That means the conclusion is that for this function e power t square, we cannot compute the Laplace transform, and that is the point of discussion here, that which class of functions we can actually find the Laplace transform. So, which class of functions the Laplace integral converges? For that, we need to just recall the piecewise continuity, which was already discussed in this earlier lectures on Fourier transform. So, a function f is called piecewise continuous, where if there are finite number of points t 1, t 2, t n between this a and b, such that f is continuous in each open interval a to t 1, t 1 to t 2, etc. And moreover, the following limits when t approaches to a plus, so from the right hand, because here we are starting with a only. So, this limit should exist. At the other end, from the negative side, that limit from the left hand side, this limit should exist, and at all other points, both from the right hand, from the left hand, both the limits should exist for all such points. and then we call that the function is piecewise continuous. For the piecewise continuity, there are two conditions. One, that the function must be continuous in each these open subintervals, and at all these points where we have either the function is not defined or the function is not continuous, in those cases at least this limit should exist, and then we call that the function is piecewise continuous. So, a function f said to be piecewise continuous on this whole interval 0 to infinity if it is piecewise continuous on every finite interval 0 to b, and if we can do this for any b from this real positive, then we call that the function f is piecewise continuous on this interval 0 to infinity. Well, so we have this example here, the function defined by this f t as 1 over 2 t and the t plus 1 in this interval 2 to 3 and 1 over 2 minus t in the interval 0 to 2. So, this is not piecewise continuous, and the reason why it is not piecewise continuous, because if we look at this limit here when t approaches to 2 from the left hand, this is approaching to infinity, 1 over 2 minus t, this is approaching to infinity. So, that is the reason we do not have this finite limit at some point here at 2. So, this function is not piecewise continuous in this interval 0 to 3. Hence, the function is not piecewise continuous because this limit here f x x from the left hand does not exist. And check now whether this function is piecewise continuous or not, because here we have at t not equal to 0, the function is defined as this one and otherwise it is. So, at t equal to 0, basically this is 0. So, here we may have problem at t equal to 0. So, just to check, the given function is continuous everywhere other than 0, because we have these quotient of two nice functions. So, it is continuous other than t equal to 0. So, we do not have to worry about the piecewise continuity of the function there, but we need to check this limit point. That means, at 0 we have to check the limit from both the ends. That means, but if we do so, because this 1 minus e t over this t, and if we take the limit t approaches to 0 from any end. So, this is 0 by 0 form. So, we can use the L'Hopital rule, which says that this is minus with plus, so e power minus t, and then we have 1, and then the t goes to 0. So, this is e 0 1. So, 1 over 1, then we have this 1. So, the limit from the both the ends, it is 1 there, it is a finite limit, and at all other points there is no problem as such. So, this function is obviously piecewise continuous then in this whole real axis. Well, the other class of functions we will consider before we go for the final theorem, it is a functions of exponential order. So, what are these functions? A function f is said to be of exponential order alpha if there exists constant m and alpha such that for any t naught greater than 0, we have this condition that f t, the absolute value is bounded by m and e power alpha t. So, the function is bounded by exponential function actually. So, m times the exponential function alpha t for some t greater than t naught, I mean for all t greater than t naught. So, if this happens for all t greater than some t naught, in that case we call that this function is of exponential order. So, if there exists a constant m and this alpha such that for some t, the t naught could be a large number, there is no problem, but there should exist a t naught also, that so that for all t now from that point onward this f t is bounded by the exponential function. So, in other words, or which is a equivalent definition which is rather used for knowing whether it is exponential order or not, or testing the function whether it is of exponential order or not. So, a function f t is said to be of exponential order if we compute this limit here t to infinity e power minus alpha t f t If this comes to be a finite number, a finite quantity, then we call that the function is of exponential order, which is exactly equivalent to this one, because if we look at this and e power minus alpha t, if you multiply both the sides, so we are getting there that this number here e power minus alpha t f t is bounded by this constant m, and for all t it should happen for all t greater than t naught. The main issue is when t approaches to infinity, because this is where it can actually go above this exponential function. So, we want to bound the function behavior as t approaches to infinity by the exponential function, and for that we are talking about these exponential order. So, our concern is now that what is happening at t approaches to infinity, because here we stated here that for all t, but the main problem will be just for when t approaches to infinity. So, actually we are looking of the function behavior when t approaches to infinity. When t is finite, there is no issues as such. Later on we will realize in this sufficient conditions where we need the functions of exponential order, and actually we need to control the behavior of this function as t approaches to infinity, and for that we are talking about this exponential order. So, if this limit with this exponential minus alpha t, the product with this f t is a finite quantity, that means this function f t is of the same order like e power minus alpha t, and then we call that the function is of exponential order. Geometrically, it means that the graph of the function f in this interval t naught to infinity. So, again the important point is this infinity. So, from t naught to infinity does not grow faster than the graph of the exponential function. So, if we have this function f, which is suppose growing like this, and we have the exponential function. So, this is exponential function alpha t, and this is our function f there. So, what is important that after this t naught could be very large, but after this t naught, this e power alpha t is growing faster than our function, which is the function f t, the given function f t. So, in this interval it does not grow faster than the graph of this one. So, after some here in this range from 0 to t does not matter, the exponential function was below the function f t, but after some point here t naught it could be very large number, but still if we, as I said before, we are talking about its behavior at infinity. So, if we can have a very large number t naught also, where we have this condition that from that t naught onward the exponential function is the graph of the exponential function is above the graph of f t. So, that is what we have the functions of exponential order, but for testing the functions of exponential order, this definition will be very useful to get this limit, and if it is a finite quantity, we say that the function is of exponential order. So, now for instance, we can show here that t power n, these functions for any value of n has exponential order alpha, and alpha can be anything positive, and this holds for any natural number n. So, this t power n is an exponential order alpha positive, which we can show with this help of this limit. So, we will take this limit t to infinity e power minus alpha t with this t power n. And now, here we see that if we write this t power n, then e power this alpha t. So, this is going to infinity, that means, and this is also going to infinity. So, we have the situation infinity divided by infinity. So, we can use L'Hopital to compute this limit, and it turns out to be, because we have here the t power n and then e power alpha t, and we keep on applying the L'Hopital rule. So, in the first occurrence we will get n and then t n minus 1, and here we will get alpha and e power alpha t, and then we have to again apply the L'Hopital rule, because the same situation infinity over infinity is happening there. So, when we keep on doing this, here we will get n, n minus 1 and so on, at the end the factorial n, and then this t will disappear there, and here we will get this alpha power n and again this e power alpha t, and we have to consider again t approaches to infinity. So, in this case as well, when t approaches to infinity, this will go to 0. So, we have this limit here is equal to 0 as t approaches to infinity. So, hence this function is of exponential order, that is clear now from here. And for instance, this e power t square, which we have also discussed before, that the Laplace integral does not exist if we take this function e power t square. So, in this case we will show that actually this function is not of exponential order. So, for this given function, if we try to compute e power minus alpha t with this e power t square, then what is happening here, e power t and this t minus alpha, and we are letting this t to infinity. So, whatever alpha we take, however large alpha we take, this will go to infinity only. So, it is not going to any positive, any finite number, it is going to infinity for any value of alpha, and therefore, this function is not of exponential order. So, the given function is not of exponential order. Now, we are coming to the main result of this lecture, and that is the sufficient conditions for a Laplace transform. So, what we have, if f is piecewise continuous, that is the first condition here, the piecewise continuity, and the second condition is the exponential order alpha. So, if we have these two conditions, or a function satisfy these two conditions, piecewise continuity and exponential order alpha, then the Laplace transform exists for this all real s greater than exactly this number, this order alpha. So, that is a most important theorem which tells about the sufficient conditions. These are not necessary conditions, we will be discussing later on what do we mean by necessary and sufficient. So, here under these two conditions, or these two conditions are sufficient to find the Laplace transform of a function. And we can look at the short proof also. So, since this f is exponential order alpha, and we know as per the definition what do we mean by the exponential order alpha, that means this f t can be bounded by m1 e power alpha t for t greater than some t naught. This was the definition of the exponential order, and the function is also piecewise continuous. So, in this case, if the function is piecewise continuous on this interval 0 to infinity, then we know that we can bound this function f t by some number in this interval 0 to t naught, because that is the beauty of this piecewise continuous function. All these limits exist at all the points where the function is discontinuous. So, we can actually bound the function whatever t naught we are talking about there, the function value we can bound by m2. So, that is coming because of this piecewise continuity, and then we have, because of the exponential order, we have t greater than t naught, this m e power exponential. So, it is bounded there when t is greater than t naught by the exponential function, and in the range 0 to t naught it is bounded by this m2. So, we can combine these two inequalities, because one says that the function is bounded by this exponential function when t is greater than t naught, the other one says that the function is bounded in this interval 0 to t naught. So, combining the two, we got that the absolute value of this f t is bounded by m and exponential alpha t, because here it was anyway bounded by, is a bounded function for 0 to t naught. So, that is not the concern, but for t greater than t naught it is bounded by the exponential function. So, for all t actually this is bounded by this m e power alpha t because of these two reasons. We can find this m accordingly based on this m1 and m2. We can choose, for instance, the maximum of the two, then this m will serve the purpose that it will be satisfying this inequality as well, and naturally this inequality. So, we have the function f which is bounded by m e power alpha t in the whole range t greater than 0, and in the range 0 to t naught, actually this helped the piecewise continuity was responsible to have such inequality, and in the range from t to t greater than t naught, this exponential order helped us to get this inequality that f t is bounded for all t greater than 0 by m e power alpha t. So, having this result, having this boundedness result on this f t, now we can discuss this absolute with the absolute value, this Laplace integral, and assuming that s is a complex number. So, we can consider a more general case. So, we have e power minus x plus y t, and then here this f t is replaced by m e power alpha t, because in the whole range 0 to r, this is bounded by m e power alpha t. So, we can bring this m outside, and then we have positive numbers there, the exponential functions. We have e power minus x minus alpha t, and the absolute value of e power minus I y t, this will be 1. So, here we have this result now, and now on integration of this, because we can integrate this, we are getting here m over this x minus alpha and m over x minus alpha with this e power minus x minus alpha r. So, and now we will let this r to infinity to get exactly the Laplace integral. So, if r to, we let r to infinity, and we note that the real s is greater than this alpha. So, assuming that this x is greater than alpha, we have this positive number here with this r, and if r is approaching to infinity, this will go to 0, and hence we will get only this m over x minus alpha. So, this absolute value of this Laplace integral with the absolute value of the integrand, what we have this m over x minus alpha. So, this is bounded, and that is what we want to show, that this Laplace integral exists, because this exists now with the absolute value indeed. So, naturally without absolute value this will exist, because that value will be smaller than this value. So, here what we have shown, that under these two conditions, that means the piecewise continuity and the functions of exponential order, if we have these two conditions, this such integral can be bounded by this m over x minus alpha for this real s greater than alpha, real s greater than alpha under these conditions. So, we have this m over x minus alpha, the integral is bounded, meaning the integral, the Laplace transform of such functions exists. Well, so some deduction from this derivation. So, we have seen that this 0 to infinity power minus s t f t dt, which can be bounded by we can bring this absolute value inside, and we have seen that this is bounded by m over real s minus alpha. That was the last conclusion, where we have concluded that the Laplace transform exists. So, here with this inequality, what we can deduce now, that when this real s goes to infinity, for instance, this is m over real s minus alpha. So, if we let this s to infinity, this Laplace integral is bounded by 0. That means, the integral 0 to infinity e power minus s t f t and dt is equal to 0. That means, the Laplace transform of f t will go to 0 when this real s, or if we are talking about only the real number, that means s tends to infinity. So, that is a nice deduction here, that if we have the functions of exponential order and piecewise continuous, their Laplace transform will go to 0 as real s goes to infinity, or s goes to infinity in case of real s. So, since we have this Laplace transform is f s, what we notice from here, that it has to go to 0 if this real s goes to infinity. That is the deduction coming from this above inequality. So, if we know that, or if we find that a Laplace transform of f t does not go to 0, for instance, as s goes to infinity or real s goes to infinity in general case, then this f t cannot be piecewise continuous function of exponential order. So, we should understand this, because we have proved here that if f is exponential function of exponential order, if f is a piecewise continuous function of exponential order, in that case we have deduced here that the Laplace transform will go to 0 as real s or s goes to infinity. But if we notice in some problem that the Laplace transform for f t does not go to 0 as s goes to infinity, then we are sure that f t cannot be the piecewise continuous function. I mean the function whose Laplace transform is not going to 0, that f t cannot be a piecewise continuous function of exponential order. That is what we can definitely deduce if we find that the Laplace transform is not going to 0 as s approaches to infinity. So, for example, the functions like f s is equal to 1, we will see later on that we have the Laplace we have some functions whose Laplace transform is 1, for instance, or s over s plus 1. In either case, so this is also not going to 0 as s approaches to infinity, because this is a constant value 1, and here also it is a s over s plus 1. So, we can write s plus 1 minus 1 over s plus 1. So, this is 1 minus 1 over s plus 1. So, if this s goes to infinity, here also this is not going to be 0, it is going to 1. So, in either case here this is given 1 and this is going to 1, not going to 0. So, these two functions, the functions whose Laplace transform is given as f 1 s and f 2 s, they cannot be piecewise continuous of exponential order. This is what we can deduce, and later on we will see that indeed those functions whose Laplace transform are given by such these functions are not piecewise continuous of exponential order. So, if such as this are not Laplace transform piecewise continuous function of exponential order, because in either case these f 1 s and f 2 s, they are not tending to 0 as s approaching to infinity. Now, just a note here that this piecewise continuity and this exponential order, these two conditions, they are sufficient conditions for the existence of Laplace transform. They are not necessary conditions for the existence of Laplace transform. So, what do we mean by this? If one of or both the conditions are not fulfilled by a function, it can still has a Laplace transform. That is what we mean by sufficient conditions. So, under these conditions definitely the Laplace transform will exist. So, these are more than what we actually need, but we do not know the necessary and sufficient conditions. We know only the sufficient conditions under which we are sure that the Laplace transform will exist. But if there are functions whose there are functions, if they are not piecewise continuous or they are not of exponential order, still the Laplace transform may exist. So, if these conditions are satisfied, then the Laplace transform must exist. If these conditions are not satisfied, then Laplace transform may or may not exist. We can observe this fact with the following examples. So, we have two examples now which can tell little more about these sufficient conditions and the remark we have made here. So, first example we will take where the function is not of exponential order, but Laplace transform exists. So, here in this case, for instance, if we take f t as 2 t e power t square and we have here cos e power t square. So, we have already seen because e power t square is coming here, and this cannot be bounded by the exponential function of order alpha. So, here this because of the presence of e power t square, this function is not of exponential order, not of exponential order. So, we have this example here which is not of exponential order, and now if we compute this Laplace transform, that means e power minus st 2 t e t square and cos e t square dt. So, we can integrate this by parts. So, e power minus st, and then here this cos will become this sine, and this e power t square is sitting, the derivative is sitting there. So, we can integrate this easily to have this sine e power t square, the limits 0 to infinity, and then we have this s there because this has to be differentiated. So, e power minus s and e power minus st and then minus s. So, that minus s and this minus will become plus. So, we have e power minus st and then sine e power t square. So, what we note now, so we have Laplace of f t, this is when t approaches to infinity, this will go to 0, and when this t goes to 0, we will get just minus sine 1. So, we have minus sine 1 because of this first term, the second term s, and you notice that this is the Laplace transform of this function e power t square, because e power minus t minus st, and then we have here a sine e t square. So, this is the Laplace transform of this sine e t square, where product with this e power minus st, and then we have s there. So, Laplace of f t is minus sine 1 s the Laplace of sine e t square. So, what this example shows, the Laplace of this e t square exists because of our sufficient conditions. This sine e power t square is a continuous function and bounded function. So, it is a piecewise continuous and of exponential order function, and the sufficient condition says that its Laplace transform will exist. So, this exists because of due to sufficient conditions, the function is indeed continuous and hence piecewise continuous, and the function is bounded. So, hence it is of exponential order. So, the second term has the existence, and first is minus sine 1, that means the Laplace transform of f t exists. So, this example shows that the Laplace transform of a function which is not of exponential order, this exists. The second example, we will show that this is not piecewise continuous, but the Laplace transform exists. For example, if we consider f t 1 over square root t, and f as t approaches to 0, we know that this will go to infinity. So, this f t is equal to 1 over t does not this limit does not exist, and it is not a piecewise continuous function, but the Laplace transform of f t, which we have already derived this formula, it is t power minus half, and that says the gamma half over this square root s. So, we have this square root pi, the gamma half is square root pi over this square root s for s positive. So, we have the Laplace transform for this function which is not piecewise continuous. So, again this piecewise continuity and the exponential order, these are the sufficient conditions, these are not necessary condition for the existence of Laplace transform. So, this example again shows that the Laplace transform of a function which is not piecewise continuous and its Laplace transform exists. So, these two examples we have or clearly shows that the conditions given in exercise in this existence theorem, that means piecewise continuity and exponential order, they are sufficient, but not necessary conditions. Well, so these are the references we have used for preparing this lecture, and now coming to the conclusion. So, we have discussed in this lecture sufficient conditions for the existence of Laplace transform, and in particular the piecewise continuity of the function and the functions of exponential order, they come to this class where we can find the Laplace transform. But just remember that these are the sufficient conditions, the piecewise continuity and this exponential order, these two are sufficient conditions for the existence of Laplace transform, but they are not necessary. If a function fails to have one of these conditions, whether the function is not continuous or the function is not of exponential order, still we can find its Laplace transform. And we have seen indeed two examples, the one function which was not piecewise continuous, and we are able to find the Laplace transform. In the other case, the function was not of exponential order, and we have seen the existence of Laplace transform. So, that is all for this lecture, and I thank you for your attention.